Hello everyone. This next lesson we're going to look at thermal energy concepts. So what they used to think, current descriptions, what specific heat capacity of different substances means and what some numbers are, how to work with them, and so on. So here we go. Before we get going on the new stuff, let's get this review question here. Okay, so you can press pause and try this one, and I'll go and show the solution of this. So here we go. We have a mass falling 60 meters. What kind of velocity would it have in the end? Right. So the work you should do if you're to use uniform acceleration concepts, you have to calculate the final velocity directly that way. Or if you use energy concepts, you'd be able to say that the gravitational potential energy is just converted into kinetic. You'd be able to cancel out the masses. Here the mass didn't matter anyways because acceleration due to gravity doesn't depend on mass, right? The amount of gravitational potential energy or the amount of kinetic energy depends on the mass, but the actual velocity doesn't, of course, right? So yeah, that's how it works. You can cancel the masses, put in your acceleration due to gravity, your mass, and solve for the velocity. So we end up with this 34.3 meters per second. Either way you do it. So the next thing I want to do is look at a video physics, or basically physics in the world around you kind of thing, right? So we have this roller coaster that drops 60 meters, right? So the roller coaster drops 60 meters. And so what velocity should it have? Well, our opening question showed that it should have a velocity of 34.3 meters per second, which if you multiply by 3.6 should be 123.5 kilometers an hour. So what we can do, because we have a video of this thing, we can use video physics where we can see what the velocity really is. Okay, so this is the video. Roller coaster called the Wild Thing, wherever it is. So they have like the start of the roller coaster at whatever frame it was, all the way through to the end of the roller coaster at whatever frame it was, right? And so it's pretty easy because the video has a certain number of frames per second, and the frame number for the front was 27, and the frame number for the end was 173. So it's a total of 146 frames. Well, we've got this ratio of 240 frames to 1 second. So we've got 146 frames to an unknown number of seconds. And so you just look at the fact that you would divide by 240. I always show students that the second number divided by the first number. So in this case, it's easy to tell to divide by 240 anyways, but this idea of always doing your second number divided by your first makes it easier if the numbers are weirder. If this was like a 7.2 or something, you know, like what would you divide by? Well, it would be 7.2 divided by 240 would be your number that you're multiplying by, really. Second divided by first. Anyways, long story short, that gives you 0.61 seconds. Well, we've got 0.61 seconds. And if we know the length of the train, like the roller coaster, and we know the time, well, we calculate the velocity. Right? So it ends up with a velocity of 32 meters per second, which obviously is a bit less due to friction, heat, sound, energy loss, quote unquote losses, right? Energy that transforms into forms that aren't usable. Yeah, so not a ton of friction there, really, I guess. It's not huge, not a huge difference, but we can analyze that difference. So basically, how much energy was lost due to heat? Well, you need mass for that, right? For amount of energy. So let's just assume if it was 1,200 kilograms, then you could calculate out how much energy. So yeah, this is how much energy it should have, right? If you had the 34.3 meters per second, it should have this much energy. Instead, it only has this much energy because it only has a velocity of 32, right? So you can do final minus initial and get how much energy was lost due to friction. Notice that if you did it the wrong way, if you did the 34 take away the 34.3 take away the 32, you'd have your change in velocity of 2.3. So 1 second, there's someone at the door. All right, so as you can see, if you incorrectly put in delta V, 1/2 mv delta V squared or whatever, you'd have a very different answer. instead of the correct 90,494 joules, you'd be thinking it's only 3,174. So very, very different math results there. So, and if you were to calculate like the friction force, you just have to know the, I guess we know the length of the track, right? So actually, no, we don't. We didn't calculate it yet, but we could, right? So if we knew the angle, we'd be able to calculate the length of the track and calculate what the friction force was, right? Easily enough. All right, so that's old news. That's stuff that we've seen. Let's look at some of the really old news, I guess, the history of how our understanding of thermal energy came about. So the earliest concepts to do with heat and energy and matter and so on were the, crazy enough, the earth, water, air, and fire. They literally thought that everything was made up for a while. They thought everything was made up of earth, water, air, and fire. So if you think about wood, it's solid, so it contains some earth. It has moisture. If you squish wood, it kind of liquid squishes out sometimes, or wood's burning. Sometimes water bubbles out of it, so it contains some water, which it literally does. You can compress it, so it has some air, and it can burn, right? And so it must have had some fire in it, whatever that means, right? So as crazy as that seems, it's actually really what they were noticing was states of matter: solid, liquid, gas, and plasma, right? So you've probably seen a plasma ball places. And lightning is plasma, fire is plasma. Plasma, well, I'm not going to talk about all the states of matter, but plasma, the only one that's like kind of less obvious is the electrons are free from some of the electrons are freed from the atom because they have so much energy and they bounce around independently, right? And then when they go back to the atom, they give off the energy they had as light, right? Yeah. So after that, there was the phlogiston. I might not be pronouncing that right. I wasn't around back then to know how they said it. But basically, this person, George Ernst Stahl, proposed that there was a fluid, a quantity, a stuff that flows out of a substance during burning, right? Really, what they're talking about is energy, but they just didn't know about it yet, right? They didn't know how to talk about it and communicate it and so on. Double check here that things are recording. Yes, they are. Good. I've done that before. I missed hitting resume. That was annoying. So clearly something is coming out of what is it burns. It's actually energy. It's not a substance, right? But they're doing the best they could at the time, right? So this theory got abandoned. This date range here, when this scientist Antoine Lavoisier showed that you need oxygen. So it's not just for burning, you need oxygen. So they started to know about the elements, and chemistry knowledge started to grow, right? And so they realized, well, it's not just something flowing out of it. It's actually a chemical reaction of some sort going on. Fast forward to this date range here, and you've got some experiments being performed, and they found that things can heat up and not change mass. They found that they realized that energy changes forms but doesn't disappear. Conservation of energy concept was realized. That heat spreads out by conduction and probably convection and so on too. So they proposed a new theory where we have this invisible substance, caloric, which again, energy, right? Just words at this point, has no mass, can't be created or destroyed, and has self-repulsive forces. So supported by lots of observations, except for things which create heat, right? So basically, this didn't really take into account the idea of friction. And so one step further was needed. And so James Joule, the name that we still give credit to, of course, realized the idea of mechanical work and the transferring of thermal energy and so on. So he began to look for a mechanical equivalent of heat, which of course was found to be work equals force times distance, right? So that led to, well, eventually a little bit of a disconnect there, but the idea of the energy of particles being like you push on something, you give it energy, right? So that led to kinetic molecular theory. And so you've probably heard of this, that thermal energy is really just the kinetic energy of molecules of a substance. So what's the difference between a cold potato and a hot potato? Just the molecules of a hot potato are vibrating back and forth faster than in the cold potato. So heat is the transfer of energy, right? Heat is often used incorrectly to mean thermal energy, like as thermal energy. So if you say something gives off a bunch of heat, well, we kind of should be saying is it gave off a bunch of thermal energy, right? So hot water, dissipates into a room. It's giving its thermal energy to the room. The actual transfer of thermal energy is called heat. So if you're saying it gave off heat, you'd say it's giving off thermal energy. You're redundant. You're saying it kind of twice. This one. So this is just a gizmo that shows kinetic molecular theory. We don't have to really do this one fully here. I had this open. I wonder if I can find it quick here. Pause quick here and I'll find it. Right here. Here we go. All right, I got it right here. So if we look at low temperature gas, they're not jiggling around very fast. And you probably want to see them actually like individually jiggling, right? But it's just a simulation. And then go to high temperature gas, they're bouncing around way faster. And again, individual jiggles would be probably a better animation of it. But so moving on to heat and the transfer of thermal energy. Okay, so there's an equation that is Q equals mc delta T. Delta T is your temperature change. It's the mass of the stuff you're changing the temperature of, and C is the specific heat capacity. So different substances require different amounts of energy to change their temperature, and Q is for some reason used. It's really just delta E. Right? It's and if you did like delta E TH, if you will, for change of thermal energy, transfer of thermal energy, that's what Q is. So yeah, just final energy minus initial energy, change in thermal energy, right? Specific capacity is just in joules per kilogram degree Celsius, if you look at the way the units would be. So it's the amount of energy needed to raise 1 kilogram by 1 degree Celsius. And that's all it is. So if we look at a bunch of numbers for this, you can see that water is a really high specific capacity. But it's used in engines to cool them down. Basically, the water goes in, gets hot, and then it goes out to the radiator, and the thermal energy that it has from that it took from the motor and the engine gets blown out, carried away by the air that's blowing past it, and so on. Yeah, water is one of the biggest ones around. I think there's some metals that have higher, but well, maybe not actually. Yeah. Anyways, water's, I don't know what the highest is. You have to Google it, I guess. Anyways, so there's gases have different quantities or different heat capacities as well, and so on. So this is a trick question, but just think about what you would think in terms of thermal energy. What has more thermal energy? A hot cup of coffee that could burn you if it spilled on your leg or whatever, or a cold, very big swimming pool. And it's a trick question because obviously this energy is very concentrated, and so it has potential to hurt you. But in terms of actual amount of energy, we're talking about two different things, right? So temperature is just the average kinetic energy of the molecules, as you saw in the little simulation of the applet, right? So the average would be, of this would be around 100, right? Thermal energy is the sum of all of them. And so if you added all those up, you'd be around 600 joules, right? If you had, one, two, three, six molecules and so on. If you add it all up, you'd have 600 versus the average is only around 100, right? So a hot cup of coffee has high temperature. Each molecule has a lot of kinetic energy, but there's not very many molecules in comparison to a pool, right? So maybe each one has 10,000 joules, but there's only like 50 of them. Versus a swimming pool, maybe each one has 2 joules. It's very cold in comparison, but there's like a billion of them, right? So yeah, there's a lot of thermal energy in large bodies of water, and that's why you have like lake effect snow and if you're next to a large, I grew up in Sault Ste. Marie, so next to Lake Superior, the temperature in Sault Ste. Marie is different than it is, hundreds of kilometers away from the actual lake, because you have this large body of water that has a ton of thermal energy, and so it has the capacity to um, warm up cold air in the fall. I get that right, and it has the capacity to cool down warm air in the spring. Moderates the climate. So here's a neat question. If the thermal energy required to raise water, so a kilogram of water, from 0 to 100, basically to boil it, so stick cold water in the microwave and bring it to a boil, okay? So if that energy, instead of raising the temperature, was given to the water molecules as velocity, as kinetic energy, how fast would the water be going? And we have the ability to calculate this now. It seems like a complicated question, but it's actually not that hard, because really you just have to think about how you have to figure out the amount of energy transferred, or in other words, the heat, right? So this is redundant to say this, but it's just kind of the way people use the language, right? So the amount of energy transferred to heat up the water, heat actually means transfer of energy. So I could have said to raise the temperature of the water, right? I'm just pointing out how the wording is kind of confusing in the world around you. So may as well get you ready for it, right? So if we had Q equals mc delta T, we've got a mass of 1, we've got the specific heat capacity of water, and we've got that temperature change of 100, bringing it from 0 all the way to boiling. So if we calculated that, we'd have this many joules of energy, fair number of joules, okay? So what is that, 418,600 joules. If we now said, okay, well, what if that energy was kinetic instead? We're literally just saying, okay, well, that amount of energy is kinetic energy. What would the velocity be? So we're multiplying both sides by 2. We are taking the square root eventually. I think I left a spot there for me to multiply by 2. Oh, actually, just multiply by 2 gives that, and then I left a spot for the root stuff. So technically plus or minus, but we don't care which direction it's going. And so we end up with root there. We end up with 914 meters per second. Multiply that by 3.6 is over 3,000 kilometers per hour, almost 3,300 kilometers per hour. That's crazy. The amount of energy is pretty easy to do. Take a kilogram of water and a liter of water and put it in the microwave, and I don't know, a minute and a half later, it's boiling, right? That microwave is generating or transferring a lot of electric potential energy to thermal energy. If you somehow could make the water move fast, it would be going thousands of kilometers per hour, which is kind of mind-boggling. I had the mass in there just to make it easy, but notice that we calculated the actual thermal energy and then, first, and then used the kinetic formula to convert, but we didn't need the mass because we've got that same mass at the beginning and the end, right? So we get that same number. So just watch for that, okay? If you don't have the mass, you might think you can't do it, but you can. All right. Another neat one here. Gizmos to the rescue again here. We've got a 10 kilogram mass. It's going to drop 1,000 meters, and that energy through the pulley and the whatever is going to turn a propeller in here. So basically the energy of that drop is getting transferred to the liquid, okay? And so the question is, what would the temperature increase be? And again, this seems like it'd be complicated, but you just have to do the work to do with thermal energy. So we have a conservation of energy concept here, where the amount of energy in this closed system stays the same. So the initial energy is gravitational, the final is thermal, right? So we've got our mg delta h equals mc delta t. It would be tempting to cancel those masses. In fact, full disclosure, I did at first when I was doing the math for this, and I was getting the wrong number, and finally I realized, oh, there's different masses. So we've got a 10 kilogram chunk of mass, and then we've got the 1 kilogram of water, right? So it doesn't make sense to cancel them out, of course, because they are different masses. Anyways, solve for delta T, and you get 23.45 or so, depending on how many decimals you're trusting, right? it would be silly to try and trust a ton of decimals because, of course, it's hard to actually have a closed system. Thermal energy escapes and goes away into the environment and so on. But the simulation shows this idea here. Okay, so let's reset here. Be 1,000, has to be 10, temperature needs to be 0, and so on. And we can look at the graph of the table of numbers. So we have the initial temperature is 0. We just press play, and you can see the temperature increasing on the thermometer simulation all the way up to 23.45 degrees Celsius. So our understanding of the physics matches the simulation's understanding of the physics. Right? So you see this and you say, wait a minute, that means we could eventually, in theory, boil water just by stirring it. And so this guy, Action Lab, he's pretty awesome. He said, he has a video where he's like, can you boil water just by stirring it? Is his video. And I think I have, which one is it? This one? No, that's the video for the train. So I have it ready to go. Then here we go.
Okay, today I'm going to be seeing if you mix water fast enough, you can get it to boil. So I got the idea for this video because one of the users named Pirate Caribbean, I think that's Captain Jack Sparrow.
So basically just, he's talking about what we're talking about, right? So here we go. He gets the Blendtec 3000 or whatever it is, and he's blasting it with the blender, seeing if he can get it to raise temperature at all. I think at one point his thermometer gets mangled. But so here we go, 117, and he basically starts to fast forward things here. It's up to 158, and so on and so on. So can't quite see it there, but it eventually gets
hit by the blade.
there we go. But it's steaming like crazy, and it's literally just because of the stirring.
Oh, yeah, that was getting hot.
So a whole bunch of electric potential energy is getting transferred by turning a motor, and then that physical energy, same as if we had a mass on a pulley and so on. So it's real. It just doesn't seem real because the amount of temperature increase is very small normally because the specific heat capacity of water is so big and there's not a lot of energy involved. Like there's actually a ton of energy in thermal energy. If you look in your kitchen, the devices that use a lot of electrical energy are the ones that produce heat, the ones that transfer electric potential to thermal energy. And I have to mention this one if there's this myth or this, everybody thinks that hot water freezes faster than cold water, right? Or a lot of people have heard this, at least anyways. If I ask any class if they've ever heard of this, like at least 2/3 of the class put their hand up. I think elementary teachers like talking about it. And that's in science, anything that seems surprising, of course, gets talked about, right? So here's my best friend forever here, Veritasium, talking about that. Where was that again? I had it open, but it looks like it closed on me. So let's go to my downloads.
Does hot water freeze faster than cold water? The obvious answer seems to be no, because all else being equal, the hot water first has to cool down to the same temperature as the cold water, and then do everything the cold water has to do in order to freeze. So it must take longer, right? Well, not according to the Mpemba effect. This effect is named after Erasto Mpemba, who in 1963 was a Tanzanian student making ice cream as a school project. The students were meant to boil a mixture of cream and sugar and then let it cool down before putting it into the freezer. But worried about not getting a spot, Mpemba put his mixture into the freezer immediately after boiling it. And returning an hour and a half later, he found that his mixture had frozen while his classmates had not. Mpemba was intrigued by this phenomenon and eventually enlisted the help of a physics professor, Dennis Osborne, to investigate the effect using cream and also water. And they managed to replicate Mpemba's finding and published a physics paper stating that warm water does indeed freeze faster than cold.
This is in 1969.
But Mpemba was not the first person to observe this effect. It dates back at least to Aristotle, who noted, "The fact that the water has previously been warmed contributes to its freezing quickly, for so it cools sooner. Hence, many people, when they want to cool hot water quickly, begin by putting it in the sun.
I always like the old quotes. Hence, many people so it cools sooner, or whatever. Just they have cool wordings.
Sir Francis Bacon wrote, "Tepid water will freeze more easily than water which is altogether cold," and Descartes, in his essay on meteorology, states, "We can also see by experiment that water which has been kept hot for a long time freezes faster than any other sort, because those of its parts which can least cease to bend evaporate while it's being heated."
So, of the different theories that he's going to go on about, evaporation of water is one of those. The parts which can least cease to bend. It's like, what? Sounds like pseudoscience to me, but
So the observation that hot water freezes faster has a long and illustrious history. But what is the physics behind it? Well, there are 5 proposed mechanisms related to frost melting, dissolved gases, supercooling, evaporation, and convection. First, frost melting. When placing 2 containers of water in a frosty freezer, the frost acts as a thermal insulator. And so around the cold beaker, the frost won't melt, but around the warmer beaker, it will. And this creates a conductive layer of liquid water around the base of the warm beaker, dramatically increasing its cooling rate.
So you can picture even a little bit of frost forming on the outside of the entire beaker, and it's like having a jacket on or a sweater on, right? It's going to be an insulator. You're saying hot water melts that, and so it doesn't have that insulation effect.
Now, this may be the case for some observations of the Mpemba effect, but other experimenters have been careful to insulate the base of the beaker from the freezer and still claim to observe the effect. So hypothesis number 2 is based on dissolved gases. One known difference between warm and cool water is the amount of dissolved gases. There's more in the colder water than in hot. So as warm water cools down, gases are constantly dissolving into it. But this is an exothermic process, so it should actually slow cooling down rather than speed it up. Differences in
exothermic means that it releases thermal energy, so it actually would warm up the hot water by the gases going into it. So
dissolved gas concentrations might play a role together with the next proposed explanation, number 3, supercooling. Water is meant to freeze at 0 degrees Celsius, but in reality, it may become significantly cooler than this before freezing occurs. Supercooling happens because ice needs a nucleation site, like an impurity or an air bubble, before it can form. The thinking is that water that's initially warmer may experience less supercooling and so freeze before the cold water, though the reason for this is not entirely clear.
I want to do something fun, and if you have water bottles at your house,
experience less supercooling and so freeze before the cold water.
Take a 24 case of water bottles, right, and throw them in the freezer just overnight, overnight, right? Good 12, whatever hours. Come in and take the water bottles out, and some of them won't be frozen. A lot of them will be, some of them won't be, and they will be at minus 19 in your freezer, but not a solid. And so they're in this super cooled state because they just didn't manage to make the crystal formation. So then you can actually just take the bottle, and if you open it or you hit it against something, it'll actually create little air bubbles and jostle things and make a nucleation point, and then it'll flash freeze. It'll actually freeze in a matter of like 5 seconds. You'll see it, all the crystals forming. And the temperature, by the way, would end up not the same. It would end up warmer. So it started, it was 19. It might drop or increase, I guess, to like minus 8 or something, because there's energy in the freezing process, which is a key part of the next part of this video. But yeah, definitely a cool thing to do. If you have water bottles, even just buy like a 6-pack or a 12-pack or whatever, throw it in the freezer. And if you get lucky, you'll have a few in there that are liquid. Then you can take it and go show someone, just like, check this out, and you hit it against something and it'll flash freeze. It's a neat experience.
Though the reason for this is not entirely clear. Now, although some experiments have found that differences in supercooling cause initially warmer water to freeze faster, the results are very inconsistent, and it's basically impossible to reproduce even in the same lab at the same time. Which is not that surprising, considering supercooling depends on something as tiny as a speck of dust or an imperfection in the beaker. And when you think about it, the freezing process itself is problematic, not only because of supercooling, but also because it requires a lot of energy to be given off. To change the state of water from liquid to solid at 0 degrees Celsius requires removing the same amount of energy as cooling it down from 80 degrees Celsius to 0.
That is the biggest factor right there. He doesn't quite say it yet, but basically dropping from 100 boiling all the way down to 0, right? draw all that energy. Well, dropping from 80 to 0 has to happen again in order to go from a liquid to a solid. So there's a way bigger energy difference, energy transfer or change needed than people think in water just going from 0 to, or like liquid 0 to frozen 0, essentially. Right? Liquid slightly above 0 to frozen slightly below 0, whatever. And that process being more difficult actually makes the race not the same as what you'd think, basically.
So when you think about it, the time taken for water to cool and freeze should be dominated by the actual freezing process rather than the time taken to cool the water to 0. And this is why a lot of the investigations of the Mpemba effect have ignored the unpredictable freezing process and focused solely on the time taken for a sample of water to reach 0 Celsius. So ignoring freezing, what could cause hot water to cool faster than cold?
So to me, I'm not as interested in the rest of this because it's like, well, why are we ignoring freezing? The whole question is about whether hot water freezes faster or not, right? But
cold water. Yeah. That brings us to number 4, evaporation. If you start out with 2 beakers containing the exact same amount of water, one hot and the other cold, well, the hot one will lose more water molecules through evaporation than the cold one. So once it reaches the same temperature as the cold beaker, it will cool faster because there's less water left in the beaker. But the reality is the amount of mass loss is typically less than 3%, and that's not enough to account for the very different cooling rates. Plus, the Mpemba effect has still been reported even in experiments using sealed beakers. So the 5th and final hypothesis is convection. Water cools primarily from its surface and from the sides of the beaker, with the middle remaining warmer. So the colder water sinks and the warm water rises to take its place. This is convection. Now, a beaker of warm water will experience larger temperature gradients and therefore contain larger convection currents.
So the water itself has higher convection currents, which is going to transfer thermal energy around and basically take the thermal energy from here and bring it to new spots that are cold, right? So if you're trying to like cool something down, if you've ever tried to cool down your phone if it's got hot, I've done this where I've been, surfing while my wife's driving on a long trip. And my phone gets hot because I'm using it so much. So I put it on like the cold window of the car in the winter to like cool it down, right? Well, if you move it to a new spot to cool it down some more, because you warmed up that spot, you can picture convection helping increase the rate of cooling. And then the other convection that he doesn't mention is even just the convection of the air around. If you put a cold beaker in a freezer, the air kind of might just sort of stay still around it. And if you ever sat in a pool, a cold pool, and you stay super still, right? You don't feel as cold because the layer of water that warms up around you kind of insulates you from the cold water, the rest of the cold water. And then as soon as you move your arm or something, you get this waft of cold water again, right? So the stationary air around it would be like an insulated layer. Whereas here, the air wouldn't be stationary because this air would get hot, and so it would rise and it would pull new cool air in. So there's 2 convection cooling effects that he only mentions the one here. But, yeah.
So even when it reaches the same temperature as the originally cooler beaker, well, it'll still have more convection and therefore it'll cool faster. In 2012, the Royal Society of Chemistry offered a prize for the best explanation of the Mpemba effect, and they received 22,000 entries. But even so, there is still no consensus on what causes the Mpemba effect, and recent research suggests that it may not happen at all. How is it possible that we still don't know what's happening with something as basic as the freezing of water? Well, here's what I think. People have witnessed warm water freezing faster than cold in real-world conditions for hundreds, even thousands of years. And a number of experimental studies appear to substantiate these observations, so you can't simply dismiss the Mpemba effect out of hand. But the freezing of water is a more unpredictable phenomenon than most people imagine. And there are so many variables, it's actually very hard to ensure everything is equal except the initial temperature of 2 beakers.
And the biggest unknown is that transfer from a liquid to a solid state being such a difficult process. It sometimes doesn't even happen, right? All the way down to like -19. Well, it's easy to have examples that are going to lead to the hot water freezing faster than cold water if it happens to be one of those ones where it just doesn't freeze right away. Waits till it gets to -10 or something. Right? So to me, that's pretty obvious as an answer for this.
Beakers. In 2016, a rigorously controlled study was performed and scientists could find no evidence of warm water cooling faster than cold water. In fact, warm water took measurably longer than cold water to cool to 0 Celsius, just as you'd expect. But They showed if you varied the placement of the thermocouple, the little device used to measure temperature, by just a centimeter in the same experiments, a slight Mpemba effect appeared. The scientists reviewed all the other Mpemba studies that provided sufficient data and showed that the reported effects were within the margin of error if temperature measuring location varied by just a centimeter. So there is no real evidence of an Mpemba effect. Warm water does not freeze faster than cold. And this is not just an esoteric finding about a quirk of nature. If the Mpemba effect really did exist, it would have significant implications for thermodynamics. It would mean that water molecules have a kind of memory of their earlier state or states. And that would mean having to update thermodynamic tables to include not only what the temperature of the water is, but also what it was before.
So picture our number 4,186 for water. Be like, well, that's if it was 10 degrees before, but if it was 90 degrees before, then it's, that's obviously not the way it is.
So maybe we should be thankful that the Mpemba effect, at least under carefully controlled conditions, does not exist. Because if it did, that would make thermodynamics a lot more complicated.
And it's already complicated enough. So there you go. So this right here, the idea of, what this is showing is the thermal energy to transfer or change phase from being ice to being water. So you're adding energy, right? And it stays that same temperature for a while. So if you have let's go in reverse. Let's have water, and say it's 50 degrees or something, and you put it in the freezer, and you keep coming back and checking. So it's going to be 50 degrees, and then it's going to go all the way down to like 0. Well, then it's going to stay 0 for quite a while before it becomes ice, and then it's going to decrease, because it's crazy actually. It's like, say every half hour you're checking, and it's dropping, say 10 degrees. So it went from 50 to 40 to 30 to 20 to 10 to 0, right? Well, then you keep checking, and it stays at 0 for another half hour, and stays at 0 for another half hour, and stays at 0 for, and then eventually it's ice, and then it drops down to minus 19 or whatever the freezer is, right? Because it's this energy that's coming out of there that you can't really see based on the temperature change. It's actually just energy coming out of the molecules, but not changing the temperature, which is just weird. And so something I like to point out is if you're buying ice for a cooler for your cottage or whatever, get that ice into the cooler as quick as possible. You want that ice to be like minus 19 degrees when you put it into your glass. That way the ice actually doesn't start melting right away. First, the ice starts at minus 19, and it absorbs, I guess, some of the thermal energy from the liquid in the glass, cooling the liquid. But the ice, maybe rises a couple degrees. It's still frozen. You're not diluting the drink yet if you start with nice cold ice. And so, but if you start with just something that looks like ice, but it's actually only like minus 1 degree, well, it's going to start melting as soon as you put it in your glass, right? So people that have ice makers on the counter makes ice, but it doesn't really make it super cold. So you'd be better off taking that ice from the ice maker, putting it in the deep freezer, getting it to be like minus 20. That way it actually works for what you're trying to do, right? Not all ice is the same. Something that's not known as well as it could be or should be. I've seen people like buy bag of ice, throw it in the bottom of their boat, go across to their cottage, and it's not fully melted by the time they get to the cottage, so it's still ice, right? Well, yeah, it's not as effective anymore if you're using it. Throw it in a cooler when you get to the cottage, and now it's like already only minus 1. Well, it's not going to keep the cooler cold as long, obviously. So yeah, even though I hope you're seeing that even though these seem incredibly complicated, the ideas of this, it's really not that bad. You're just just using MC delta T and converting it to whatever form. We could even do this question about the velocity it would get, like how high up would it get? You can calculate that one easily enough as well. Like how if it was raising the water, how high up would it go? I'd be curious to see if I should add that in. I'm going to add that in as a question. Plus, how high up would the water get if the gravitational potential energy was equivalent to the thermal energy yeah, heat to raise from 0 to 100 degrees Celsius. Right? Calculate that. All right. So, as always, thanks for watching. I hope that makes sense. And yeah, see you next time.